Great.
So, well, thank you very much for coming to another seminar. Today we have Horacio Serna. He is a visiting postdoctoral researcher from the University Computational. Getting something, muting the YouTube. Okay. So, and he's visiting, working with Marco and the video group. So, thank you very much, Horacio, and the floor is yours.
Thank you for the kind introduction, and thank you for allowing me to present my work here. So, well, first of all, I would like to, I'm gonna have to pass by this. This is the microbial devices I've been using. So you can just check them. I will talk about them afterwards. And yeah, the title of the presentation is When Active and Passive Matter Meet, exploring active-passive mixtures at the microscale. So this is the outline. I will give first like an introduction, a general introduction of soft matter, passive matter, active matter, what it is. Then I will talk about the system I'm working on currently, and the results, and finally the ongoing work. So first, let's talk briefly about soft matter, right? There is a pretty simple definition of soft matter. It's just a material or substance that is able to, or you can deform when applied like low forces, right? So for example, the flesh, our flesh is soft matter, right? And there are like different, there's a classification of soft matter. You have colloids, polymers, amphiphals, proteins, macromolecules, all the stuff is included in soft matter. But I would like to draw your attention to colloids, right? Colloids, basically they are made out of two phases, right? And the definition is when you have one phase and you disperse that phase into another, then you have a colloid. The phase which is dispersed usually is it's made out of small particles, right? Pretty small particles are small, but not that small as molecules, right? So it's like a mesoscale, let's say. And depending on the nature of the dispersed phase and the nature of the dispersion phase, we can have different types of colloids like foams, emulsions like mayonnaise, gels, smoke, right? But I would like to emphasize on this type of colloids in which we have solid small particles dispersed in a liquid medium, right? Like paint and inks, okay? So we think about this type of matter as passive matter because their constituents, they cannot consume their energy to move or consume the energy of the surroundings to self-propel or to move, right? They are just subjected to thermal motion, and I will mention, I will talk about it in more details in a while. So that's why when you evolve this type of system, when you see how they always evolve towards equilibrium states. And those equilibrium states are dictated by laws of thermodynamics, right? So this is like the idea behind passive matter. On the other hand, we have active matter. And in this case, the constituents of the system do have this ability to either consume their energy to move, to self-propel, or to gather the energy from the environment, from the surroundings to move, right? And probably the most interesting feature of active matter is that when you have many active agents, you can observe different types of collective motion, this type of coherent and synchronous motion. And as you can see, it is present in basically all length scales. So we have from bacteria swimming and exhibiting this swarming type of motion. Here we have an example of an active agent, paramecium, which is a ciliated microorganism. Here we have ants doing this milling motion. These also school of fish, starlings doing this mesmerizing flocking. Also, shape, and why not people in a concert, right? So all those are examples of collective motion observing active matter, right? So, since these systems are intrinsically out of equilibrium, then they do not evolve towards equilibrium states, but towards steady states. And some of the steady states are basically those collective behavior we observe. So this is a nice visual way of understanding the difference between active and passive. Let's have in mind this case of colloids, which we have a liquid, right? And we put in the liquid small particles, right? So here we have the typical diffusion experiment. We have a petri dish, we have water in it, and we add a drop of a given ink, right? And we see that at the beginning the drop is there, but as time passes, it starts to diffuse, right? And in the end, the final state would be that the concentration of the ink is homogeneous in the whole container, right? However, if we think about that suspension of active agents, in this case, multibacteria, and of course, depending on different factors, like some external potential, like gravity, some maybe we have some chemicals in the medium that the bacteria are like attracted to, right? But we can see that this, let's say, diffusion phenomena, like just homogenizing the concentration, is not doesn't happen right away, right? You see that the bacteria start to form this sort of bioconvective patterns, right? So this is a nice way of see the difference of active and passive matter. So, yeah, let's keep in mind this example, the colloid embedded in a fluid, right? So in 1827, Robert Brown, when observing pollen grains under the microscope, discovered this sort of interesting behavior of the pollen grains because they were like moving in a random fashion, right? Without a clear force on them, right? They were just moving randomly like this. Then some years later, Albert Einstein theorized about it and proposed that the liquid was made of small particles, molecules, actually, right? And those molecules were hitting the colloid. And then, since these collisions came from all the directions in space, then this random motion could be explained, right? And some years later, Jean Perrin basically demonstrated experimentally that actually the liquid was made out of molecules, and this was the explanation of this random motion of the pollen grains. And this discovery actually was fundamental because after this, the atomic hypothesis was accepted, basically. So this is not, this is a great discovery, right? And this type of motion is called Brownian motion because of Robert Brown, and is the mechanism behind diffusion. So the process we just observed when this ink was spreading occurs because of this type of motion. Okay. So the idea of what I'm doing now is, okay, now we know what active and what passive matter is. What happens if we put them together in a mixture? So again, in the case of a regular Brownian particle, we observe this random walk, right? The particle is just moving in this fashion. But now if we want to, let's say, activate the particle, activate the code, in the sense that, okay, we can think about a microorganism that is able to swim. So for a very initial approximation, we can think about the bacterium as a particle that has a prescribed orientation, and in that orientation there is a force or a self-proportional velocity that is applied, and then it can move, right? Still, it is subjected to thermal motion, right? But there is another component, there's this active force which is acting. So we apply that active force in a given orientation, we observe now this persistent motion, right? Which is completely different from the random walk of a passive column. So the idea now is, what happens if we put them together? Why is it interesting or important to study these mixtures of active and passive particles, right? So there are many reasons, but I'll mention 3. So the first one is that for interaction between microorganisms, right, is sometimes this encounter, let's say, of active and passive matter occurs often, right? So it's interesting from a biological point of view. So for example, here we have a mixture of non-motile algae and motile bacteria. The non-motile algae, in this case, they will be like a passive matter because they cannot move, right? So only thermal motion is there. The motile bacteria, they can move, so active particles. But the thing here is that the non-motile algae, they are photosynthetic, so when you illuminate them, they can do photosynthesis and they will produce oxygen. The oxygen will be absorbed in the medium, and then since this specific type of bacteria exhibits positive chemotaxis to oxygen, then they will go to that region rich in oxygen, and it will end up in expelling out the non-motile algae. As you can see here, you see fluorescence bacteria, they will accumulate, right? And here you see the non-motile algae that are being like pushed. So then you will see that this region is with a lower concentration of non-motile algae. So this is one thing. It's important to understand the interactions between microorganisms. Second, from a fundamental point of view, from the perspective of physics, we basically know a lot of the thermal motion, the Brownian motion. We know that we can characterize it just knowing the temperature and the properties of the fluid in which the colloids are embedded, right? But when we study a case in which we have these passive colloids and active particles as well, then for this type of system, we do not know that much as we know in the case of thermal motion. So here we have the passive particles. You can see that they are doing this Brownian motion, but since there are some motile cells there, systemic monas, you see that when they go close to the passive colloid, they can move it, right? They can basically transport it, right? And due to these jumps, you can call it like active kicks, right? Not doing just Brownian motion, but suddenly a cell appears, push it, move it. It's like an active kick. And if we characterize like the transport of the passive colloids with the diffusion coefficient, it's a way to characterize the transfer, and we start to change the concentration of cells in the suspension, we see that clearly these active kicks, the frequency of these active kicks will increase, and then we see that the effective diffusion coefficient, right, it's increasing as well. So then there is a way to increase the transfer properties of passive colloids by including them in a suspension with active agents. Okay, and finally, since we are able to increase the transfer properties of passive colloids or passive matter via adding some active agents in the suspension, we can leverage that to develop technology, right? So here we have 2 examples. One is for cargo delivery. In this case, the active particles are synthetic. They're not microorganisms. There's some type of colloids called Janus particles. They are coated with a metal half hemisphere, right? And depending on the metal you use, you can make them like responsive to electrical magnetic fields. And the passive colloids are this here represented in red. And the interesting thing here is that when you apply an electric field, then the passive colors will be attracted towards the Janus particle, which is the active one. You can somehow direct the motion of these Janus particles, and then when you reach a place in which you want to drop the cargo, you can just turn off the electric field and then they will be released. So it's like a cargo delivery at the microscale. This is one thing. Also, we can think about sorting the mixing or separating the mixture. Here we have a microfluidic device with this specific shape. Circular chamber with this cylindrical thin channels there. Suspension of chlamydomonas, the active particles, and colloidal bits, the passive particles, is injected there. And we observe that after some time, the passive particles starts to accumulate in these thin channels, right? And then we are basically separating the passive bits, the passive colors from the suspension. So this is another way to think about the applications of this type of systems. Okay, and this is what I have been doing in the last 2 months in Marco's lab with a huge help of Sujit. And this is the microfluid device I just passed at the beginning. Contains this type of microchannels, right, with this geometry. So you have these like 2 walls, the x axis with this wavy structure, let's say, and then in the central region you have funnels like obstacles, right? And you have then we inject a suspension of active particles, which are chlamydomonas, and passive colloidal bits. And the idea here is to study how the transport of the passive bits towards the gaps. Okay, one important thing is that in principle the gaps should be large enough for allowing the passage of passive particles, but not that large to allow the passage of the cells, the motile cells, right? So in this way we can study how the curvature of the panels affects the transport of passive objects were embedded in an active suspension. Okay, and since my background is in simulations, now I will try to give you some ideas on how we can simulate these type of systems, right? So the system I'm considering here is pretty similar to what we have in experiments. We have a channel with 2 walls. In this case, the walls are flat. They don't have this wavy structure. And the funnels are just in the central region and basically the same structure as in the experiments, right? So the pink particles with the vector are the active particles, and the blue particles, the bubble particles, are the passive particles. Again, the gaps of the channels of the funnels only allow the passage of the passive particles. So we start from a configuration like this. We put the mixture in the top compartment. We leave the system to evolve until it reaches a steady state. And the steady state, as you can see, is characterized by a distribution of passive particles, which is the fraction of passive particles in the bottom compartment is larger, right? Because the active particles are pushing them out through the gaps, right? And here we have some geometrical parameters of the channels, well, of the funnels. We have the length of the branches of the funnel. We have the size of the gap, and also the angle that the funnels are forming with respect to the x-axis. So how do we simulate this? So basically we need an equation of motion. This is just Newton's second law. This is mass times acceleration equal to summation of forces. Here there are many forces involved, right? In the case of the active particles, we have this force here, which is the active force. This n vector is just the orientation of the active particles, right? And along that orientation, we apply an active force which is kept constant, Fa. Okay. Then we have this term here, which is the force due to the interactions between particles. So in this case, we are using a repulsive potential. It's given by this expression. This is not actually important. We just need to understand what it means. It's a repulsive potential. It means that when two particles are close, they just repel with each other. They just like bound out, right? And so they have like a volume or an area. Oh, I forgot to mention, this is in 2 dimensions. Okay, it's a 2-dimensional system. Okay, the next term is a drag term. It's just since we know that the particles are embedded in a fluid, when they are moving, they experience a drag force, right? It's like when you are running or swimming, you feel that drag against the resistance of the medium in which you are moving. So it's here. And finally, this weird term here accounts for the random motion. So this random motion that we discussed at the beginning, right? This collision with the liquid molecules that made the particles to move in this fashion. This is for the active, but if we are, we can write the same equation for the passive, with the only exception that then this term here is cancelled, right? Is considered to 0, right? So then the particles are not self-propelling to given directions. Okay, so the first, that was for the translational motion, the translational equation of motion, right? From this type of motion, we have initial position here, then we are moving in this space, right? But since the active particles also have this orientation, right? We need something to account for the rotational dynamics of the active particles. The passive particles do not have any rotational dynamics, completely random, but the active particles do have this. So there is a model, right, to account for the rotational dynamics of active particles. It was first described for bacteria, right? And it's called the run-and-tumble model, the run-and-tumble motion. And basically it's like a 2-stage type of motion. You can see here that the bacterium is first it moves straight in a straight fashion, then it at random it performs a tumble event, which is basically change of orientation, then it performs another run, a tumble, a run, a tumble, and so on and so forth. In the case of bacteria, in E. coli, which is a flagellated, multiflagellated bacteria, these 2 stages of the motion are characterized by the disposition of the flagella. So when they are performing a run, straight motion, they point their flagella backwards, and then it rotates, and then they can move forward. But when they are turning, what they do is they spread out the flagella. And this video from the microscope, you can observe more or less when they spread, right? The flagella turn. But some years ago, Marco and Ilan showed us that this type of run-and-tumble motion was also observing more complex microorganisms, eukaryotic microorganisms, specifically in Chlamydomonas, right? And they observed that this run-and-tumble also was related to the motion of the flagella. So when the algae were like doing this typical breaststroke motion, synchronized, they move in a run, so in a straight fashion. And when they do this asynchronous motion of the flagella, they turn. So since the experiments are done with chlamydia, so the simulations, since we can also use this model for the simulation, so it's like a nice choice for doing this type of motion. And here, this is how we implement it in the simulations. We have apparatus, not here, but it's alpha, same alpha. A parameter which is called the tumbling rate, which is basically the probability at a given time state that active particle just change the direction. And then to implement it, what we do is, okay, this theta is the angle between the orientation of the active particle and the x-axis. So what we do is we generate a random number, this zeta, right? And if the tumbling rate, which is a parameter we set in the simulation, is smaller than the random number we generate between 0 and 1, then we keep the same orientation for the next time step. But if it is larger than that random number, then we have the previous orientation plus a random angle between 0 and 2 pi. So then we produce this tumble event. Okay. So these are the results. Will be quick here. So we have a system. Initially, the mixture is placed in the top compartment of the microchannel. We let the system evolve. Here we can have the time response of this F bottom is just the fraction of passive particles in the bottom compartment as a function of time. We do that, and we realize that we can fit that time response to just first order kinetics model. It's pretty simple one. Here the markers are the data from the simulations, and the solid lines are the fits to these equations, right? Which is important here is just that from this set of equations, we can have like a time scale of the process, which is just given by this expression, right? And K plus and K minus is just, let's say, the rate at which the flow of particles, of passive particles, the K plus is the rate of flow in which the passive particles comes from the top to the bottom, and the minus the other way around, from the bottom to top, right? So with this relation, we have the time scale of the process. So we know how fast it is, basically. And here, we have some other results. First, let's imagine this. Let's imagine that instead of placing the mixture, we are placing in the top compartment just passive particles, the blue ones, the small ones. If we leave the system evolve, in the end, we will have a distribution of passive particles of 50% in the top and 50% at the bottom. We know that because just by random by thermal motion, we will have this homogeneous state, right? Now, second, let's think that we place the mixture, but the big particles are not active, but just passive, right? So we have a mixture of passive particles, of big passive particles and small passive particles. This is the case here. So this, well, here we have the fraction of passive particles, or in this case, of small blue particles in the bottom. So if we do that, we see that as we change the angles between the obstacles and the x-axis, we see that the fraction of passive particles, or in this case, the small ones, in the steady state is around 70%, right? But if we activate the big particles, the system we are studying, and we do the same, and we change the rate at which the active particles perform this tumbling, we observe this sort of behavior when we plot the fraction of passive particles at the steady state. We see a maximum, right? And actually we see that the separation, or the fraction of passive particles in the bottom compartment, increases a lot if you compare with the just passive, small passive case, or in the case of passive big and passive small, right? We go from around 70% to 92%, right? And you can see that this distribution of passive particles at the steady state does not depend on the geometry of the channel, right? The different colors are just the angles that the obstacles are forming on the x-axis, right? It doesn't depend much, at least for this distribution of passive in the top and bottom compartment. But regarding the dynamics, it does depend. This is the time scale of the process for different angles and for different tumbling rates. And we see that what we want here, if we are thinking about applications, is that we do it in the shortest time possible, right? So we see here that in the case of 70 degrees, right? And a tumbling rate around 10 to the minus 4. We have also like the best performance in terms of dynamics, which more or less coincides with the peak here, right? And the final interesting or important thing to characterize more or less this type of system is that if you take a look here, the active particles sometimes are just blocking the gaps, right? Both the concave and the convex. So we need, and of course, if the gaps are blocked, then the passive particles cannot go through. So we need to characterize this as well. So here we present the fraction of open gaps at a steady state. So it looks like this sigmoidal function. And you see that the inflection points around here coincides with the best performance in terms of dynamics and the best performance in terms of separation. Okay? So more or less to understand this, we have like an interplay of different effects. So first we need that the gaps are open. I mean that the fraction of open gaps are is as high as possible, right? But we see that if we keep increasing the tumbling rate, that's true that we increase the fraction of open gaps, but then we decrease the, let's say, the performance of the separation. So it means that if the active particles tumble a lot, then they do not have like enough persistence, meaning they cannot explore enough the top compartment, then it decreases the frequency of the encounters with the passive particles. That in the end is what is allowing the separation, right? The encounters with the passive and the active and the passive, right? So we need to take that into account. So even if we have a large fraction of open gaps, we need to keep the tumbling rate in a range in which the active particles are able to explore the whole top compartment. And if it is too high, then since they are rotating too often, then they cannot explore the whole thing. And that's pretty much the same. This is like the ongoing work. So first, in the model I just described, we are not considering the hydrodynamic interactions when the particles are moving, right? We are considering like the interactions with the liquid that are being exerted on the particles, because that's why we have this thermal motion there, right? This random force there. But we are not including the how the liquid particles or liquid molecules are being affected while the active particles are moving or are swimming in the medium, right? So for that, we need a different type of model, right? I'm not going into details, but the idea is to include the flow fields that appear when the active particles are moving in the fluid, right? And we need to keep going with the experiments. We need to refine some things. But yeah, this is also ongoing work. Yeah, that's it. Thank you for your attention. That's what I think.
Maybe you said it and I got lost in the, but I mean, in the simulation, you can change the tumbling rate distribution because it's just equal to the common distribution.
Yeah, right.
But if you wanted to build it like an application, like with the organisms, I guess that, I mean, each organism has its own motility with its own prescribed tumbling rate. So would there be, like in your, maybe you said it that way, I said maybe I got lost, but in your experiment, like you use Plamy, so it will have one distribution of alpha. So you would have one experimental condition to compare with your model, I guess. So I don't know. Maybe there are ways like, I don't know, genetic modification or something that maybe you can have like different utilities.
Maybe there are, I don't know, but maybe it's just like my thought. Maybe by illuminating the sample with some sort of light that probably exhibits for which climax it's positive or negative for the taxes.
Mhm.
It also changes the way they move. So it would be not exactly as we are changing the tumbling rate, but something that we could explore, like
Mhm.
how can we, for example, increase the separation or improve the separation by just using different light intensity or
Mhm.
wavelengths and
Okay.
something like this. This is more like a question for experimentals.
You repeat this experiment with bacteria, for example, E. coli, and expect the same result? Because I was thinking that in case of bacteria, for example, E. coli at large cell concentration, you see collective.
Yeah, this.
So do you think in that case you can see the same result? You can see the separation of acid particles in the channel.
I think that since the funnels are like a semi-permeable membrane to that effect, right? That they only allow the passage of passive. I think to some extent I would expect that, but I'm not sure if this collective motion or this bacterial turbulence or bacterial swarming that you are talking about can, I don't know if it would hinder or enhance this effect. That's something we need to look at, but I expect some sort of separation as well. It should be higher than the case of just passive and passive big particles and passive small particles. I think. Yeah.
I have a question as a non-physicist. It's like the ratio of size between the passive and active particles. Also taking into consideration, or would it have an influence? They have like a certain proportion with the sizes.
Well, for thinking about the separation, the only thing you need to take into account is that the gaps only allow the passage of the small ones. But the physics, I mean, if you think about the physics, it makes a difference, because then if you have different size of the particles, then the drag force is different. So yeah, there are some physical implications on that, right? If we change the size of the particles. But for the purpose of the separation, the only thing we need to take into account is that the gaps only allow the passage of the small ones, which are the passive in this case.
Have you considered the effect of viscosity in your simulation? Like if you have the high stress?
It is implicit there in the drag force, right? The viscosity. But no, I mean, exploring cases in which we have super high viscosity, not yet.
I have a very egoistic question, so maybe it's not of interest of anybody, because I want to do, I think, like a freelance lot. And in before you presented your experiment, the one with the clammy that was pushing the particle and modifying the effective diffusivity.
Another experiment from Mark.
Okay. Okay. And maybe,
So you have
maybe, okay.
you have the best.
Okay, now then I go and I know that because it was normalized to velocities, and I was wondering what was the.
I think it was
definition.
with the sedimentation velocity and.
No, we can talk.
Yeah, okay, because I think I need.
He's the one. Okay, so any more questions? So we can leave it here. Thank you very much. Okay, thank you.